Well, good morning, everyone. My name is Jonathan Mace. I'm from Brown. 2DFQ is joint work with my advisor at Brown and our colleagues at Microsoft Research. So, when many of us think of multi-tenancy today, we think of containers and virtual machines running on shared machines in a data center. However, underlying these, data centers today also host a wide variety of common shared services, such as storage, database, queuing, and coordination services. For efficiency and scalability, API calls from users to these cloud services execute inside the same processes, rather than being isolated into separate processes or containers per tenant. Unlike containers and VMs, OS and hypervisor mechanisms for resource isolation and fairness are ineffective in shared processes because they don't have visibility into which tenant is responsible for resource consumption. They also don't have visibility of application-level resources and tenant information. Instead, many of these systems implement a form of soft fairness at the application level using fair queue schedulers. Fair queue schedulers can be applied to this setting in the following way. Incoming API calls from different tenants are accepted and placed into per-tenant queues inside the process. A set of worker threads is responsible for processing requests. Each worker thread runs in a loop, dequeuing and executing requests. Worker threads invoke a fair queue scheduler to decide which requests to dequeue and execute each time. This gives the application control over precisely which requests get to run, avoiding context switching overheads, and efficiently supporting requests that might only be tens of microseconds in duration. However, the application lacks the ability to preempt requests once they begin executing. Many cloud services only actually implement simple first-in, first-out or other ad hoc approaches to request scheduling here. However, that approach inevitably leads down the line to things such as denial of service, which we've seen in systems like Hadoop, OpenStack, and several others. So beyond those ad hoc and simple approaches, some cloud services have had success adapting fair network packet schedulers in this setting. There is a clear analogy to network packet scheduling, in which the scheduler alternates between packets to be fair to flows that are sharing a network link. Fair schedulers from this domain, such as weighted fair queuing, can be taken and applied to request scheduling in cloud services. The most obvious difference is that a server typically has multiple threads for executing requests concurrently, whereas there is typically only one link in the networking case. This gives us an opportunity to improve the quality of service received by some tenants, because we're able to isolate short requests from long requests and avoid head-of-line blocking, sort of like this. Two-dimensional fair queuing, or 2DFQ, is our solution to this. 2DFQ is a scheduler that separates requests across threads based on their size, and also deals with the fact that we typically don't know how long a request will take to execute when we go to schedule it. To motivate these challenges and evaluate 2DFQ, I'll use workloads from Azure Storage, which is a multi-tenant storage, database, and queuing service at Microsoft. To begin with, I'm going to show you some examples to illustrate what we call bursty schedules. Suppose we have a tenant A submitting a workload of smaller requests, which might be like a fast database read to Azure Storage. And suppose we have a tenant D submitting a workload of larger requests, which might be like database table scans. If A and D are sharing just one thread, then a fair schedule between A and D would have A getting 10 requests, followed by D getting 1, followed by 10 more of A, 1 more of D, and so on. This schedule is fair to both A and D because they get the same total amount of work done in the long run. But from the perspective of A, this is a bursty schedule because A's requests execute in bursts of 10 at a time, followed by lulls where nothing executes. The ideal schedule for A would space its requests out uniformly over time like this. But due to the presence of D, it's impossible to give such a schedule to A without either being unfair or being able to divide D's requests into smaller units. This also affects A's tail latency because some requests have to wait for a long period of time before they can execute. So let's expand on this scenario by adding 2 more tenants. A and B both have small requests, C and D have large requests. Here is one example of a fair schedule in this scenario. A and B alternate one request each to a total of 10, then C gets one, then D gets one, and so on. And here's a second example of a fair schedule. A and B alternate one request each to a total of 5, then C gets one, then A and B get 5 more, then D gets one, and so on. Both of these schedules are fair in the long run as well. But for tenant A, the first schedule has longer bursty periods followed by longer lull periods, making the second schedule slightly better. The reason I'm showing you this example is because in the packet scheduling literature, initial schedulers like weighted fair queuing and start time fair queuing produced the first schedule, but worst case fair weighted fair queuing was the algorithm that came along and gave us schedules like the second, which are provably the best we can do in this setting. To see how things change for cloud services, suppose we have now 2 threads, meaning we can concurrently execute 2 requests at the same time. One fair schedule might have 10 requests of A and 10 requests of B concurrently executing, followed by a request of C and D concurrently. Let's compare the schedule to a second one. A and B alternate on the first thread, while C executes on the second. Then A and B continue to alternate on the first thread, while D executes on the second. Both of these schedules are fair in the long run as well, but the bottom schedule here is significantly better because there is no burstiness whatsoever for A or B. In fact, this is giving A the ideal schedule. So what I'm showing you here is that when we have more than one thread, we can substantially reduce the burstiness by separating tenants onto different threads. In this example, A and B never wait behind requests of C or D. The bad news is that existing schedulers, including the ones mentioned before, all produce the first schedule, because they were developed in the context of a single link where the focus is on worst case bounds. 2DFQ is our solution to this problem. 2DFQ separates requests onto different threads based on their size, essentially avoiding blocking like in the example. Oh, my clicker's gone. However, there are 2 challenges to scheduling in shared services that we need to overcome in order to produce those smooth schedules like the one that I showed. As we saw, tenants with small requests are the ones affected by bursty schedules, and the amount of burstiness is proportional to the size of the large requests of other tenants. In cloud services, the duration of a request can vary by more than 4 orders of magnitude. A second challenge stems from the fact that for many schedulers, request size is used to make scheduling decisions. However, we don't actually know this information, like how long a request is going to take to execute or the resources it might consume. Instead, if we want to use these algorithms, we have to estimate the costs based on either models of the APIs or history of recently completed requests. To illustrate these challenges, we can look at the cost distributions for different APIs to Azure Storage. This figure shows how different APIs vary in cost from only hundreds to millions of units per second, such as API G, which has an extremely high 99th percentile request cost. APIs that vary widely in cost like G are going to be more vulnerable to misestimation as well, since estimates could be wrong by many orders of magnitude. These characteristics also extend to individual tenants. If we instead look at cost distributions per tenant, we can equally see that there are tenants with a wide range of request costs, and some are going to be more vulnerable to misestimation than others. Real workloads are like a sliding scale that, given the mix of tenants present, it can contain potentially widely varying request costs and be very unpredictable. Since existing schedulers were not designed to address this dimension, they rapidly deteriorate once things stop being predictable. Our solution to these challenges, 2DFQ, does not improve upon worst case bounds, but in the average case, 2DFQ avoids bursty schedules and gracefully degrades under workloads that are less predictable. The actual 2DFQ algorithm is an extension of worst case fair weighted fair queuing, which itself is an extension of weighted fair queuing. So I'll present the algorithm assuming we know request costs and address cost estimation afterwards. So let's remind ourselves of the idea behind weighted fair queuing by going back to our earlier example with these 4 tenants. This is the schedule that weighted fair queuing ultimately produces, and I'm going to step through the process of producing this schedule. And I'll use these gauges to indicate the service received by each tenant. To begin with, each pending request is stamped with a finish time, which is calculated using the request's size. So here the finish time of A and B's requests are 1, while the finish times of C and D's requests are 10. The algorithm will pick the request with the lowest finish time to run on the top thread, say A. This leaves B with the lowest finish time to be selected to run on the bottom thread. When those requests complete, A and B have received 1 unit of work each, while C and D have received none. The ideal fair share each tenant should have received is therefore 1/2 of a unit, which I'm going to illustrate here on this gauge. These algorithms call this ideal fair share the virtual time. Going back to the requests, the finish time of A and B's next requests are now 2, which is still much less than C and D's finish times of 10, so weighted fair queuing again picks A and B. And at this point, weighted fair queuing is going to keep selecting requests of A and B until their finish times exceed the finish times of C and D, at which point C and D are finally chosen to run. C and D run concurrently, blocking both threads until completion, and thereafter the pattern repeats. So this is the schedule produced by weighted fair queuing. Let's rewind and take a look at worst case fair weighted fair queuing. It uses the same finish time criteria to select requests, so it scheduled a request of A and B each. However, we now add an element of pacing to requests. A request can't be scheduled if the tenant is ahead of its fair share. For example, A and B have both received 1 unit at this point in time, but the ideal fair share is only 1/2. Thus, we deem A and B to be ineligible, and we only consider C and D. So we schedule C and D. When those requests eventually finish, virtual time has advanced to 5.5, so A and B's requests are eligible to run again. And in fact, A and B are quite far behind their fair share. So the next few requests to go all belong to A and B. Eventually, A and B again exceed the ideal fair share, making them ineligible for scheduling, causing us to repeat this cycle of selecting both C and D at the same time. And this continues ad infinitum. So the key to 2DFQ is to make different decisions for different threads about when requests are eligible to run, in order to avoid this all the big requests or no big requests behavior. We'll rewind again and look at the schedule 2DFQ produces. Like the prior 2 algorithms, 2DFQ chooses requests with the lowest finish time and initially picks A and B. 2DFQ also uses eligibility time to pace requests, and for the bottom thread, A and B are both ineligible, just like for WF2Q, so C's request is selected. But for the top thread, we determine eligible requests by looking ahead into the future and seeing which requests will be eligible a few steps ahead. At that point in time, A and B will once again be eligible to run. So for this thread, we are allowed to include A and B in our decision. Since they have the lowest finish time, one of them will be chosen. This is the specific eligibility formula we use to determine a request's eligibility for a thread I if we have n threads. Requests are eligible sooner for higher indexed threads. So going back to the schedule, requests for A and B are going to continue to be selected, and they never get so far ahead of their collective share on this thread to be ineligible for it. When C's request eventually completes, the same logic occurs for selecting a request for the bottom thread. A, B, and C are ineligible, so D is picked, but for the top thread, A and B remain eligible, and A is selected. And from there on, the schedule repeats. The effect of 2DFQ's eligibility criteria is to partition requests across threads based on size. Small requests are always selected first, according to finish time, so they're going to be immediately scooped up by the highest index threads. So that's the 2DFQ algorithm, but it only works if we can calculate start and finish times. And to do that, we need to know the cost of requests. Our intuition for dealing with unknown costs is as follows. Suppose we have some other tenant whose workload contains both large and small requests. And if we're picking the next request for the top thread, one of two things can happen. Maybe the next request turns out to be a small request. Then once it completes, we can go back to servicing other small requests. But maybe it will turn out to be a large request, in which case we will block that thread and get a bursty schedule. And that would be a disaster. So our solution here is straightforward. If a tenant is unpredictable and varies between cheap and expensive requests, then we're going to assume their requests are always expensive. This penalizes unpredictable tenants, but it makes things better for tenants with small requests. In the paper, we show that this is okay to do for our workloads, because actually many tenants are reasonably predictable, and it's only a handful of bad tenants that are unpredictable. So moving on to evaluation, we implemented 2DFQ as well as several other algorithms, but for clarity and due to similarity in results, we present results comparing 2DFQ only to weighted fair queuing and worst-case fair weighted fair queuing. We evaluated 2DFQ in a discrete event simulator using production workloads from Azure Storage. And in the talk, I'm going to focus on showing how 2DFQ produces smooth service, first with known costs, then with unknown costs. But in the paper, we present numerous experiments exploring other dimensions and evaluating the effects on burstiness, fairness, and in particular tail latency. So in the first experiment, we'll examine 2DFQ for a synthetic workload with known costs. We have 50 small tenants, like tenant A, all submitting requests with a size of approximately 1 sampled from a normal distribution. And we have 50 large tenants, like C, with costs approximately 1,000, also sampled from a normal distribution. This is 3 orders of magnitude difference in cost. The tenants share a server with 16 threads. Each thread can process 1,000 requests per second. Running these workloads, let's look at the throughput or service rate over time for just one of the small tenants. For worst case, first, for weighted fair queuing, we can see that the service oscillates over time like this. For worst case fair weighted fair queuing, we get much more stark behavior. This service is really bursty, periods of high throughput followed by nothing. To illustrate why this is the case, we can visualize the request that each thread is running at each point in time. The lanes in this figure represent threads. Dark shading indicates the thread is executing a large request, and light shading indicates a small request. We can see that worst-case fair weighted fair queuing is oscillating between periods of only large and only small requests. Finally, 2DFQ achieves much smoother service for this tenant. Again, looking at the thread occupancy, we can see that for 2DFQ, requests are partitioned across threads based on size quite effectively, which explains the smoother service. So now we'll look at similar results, but this time for real workloads from Azure Storage. Using workload samples from 50 production machines, we randomly select 250 tenants and replay their requests on 32 threads, each with capacity of 1 million units per second. In addition, we're going to add in the workloads of these 12 tenants that we looked at earlier. In order to evaluate burstiness, we're going to examine the service received by T1, since T1 is representative of small tenants with small requests that are the most affected by burstiness. For weighted fair queuing, the service received oscillates over time for T1 like this. WF2Q actually does pretty well with only a few spikes of burstiness, while 2DFQ smooths those spikes out too and produces even less bursty service. As before, we can look at the thread occupancy over time across all tenants. Since we now have requests of all different sizes, I'm going to shade the threads based on the size of the request that is executing at each point in time, with darker meaning more expensive requests. For WF2Q, we can observe how the spikes in service down here correspond to multiple large requests occupying threads simultaneously, for instance, here and here. For 2DFQ, we can see that requests are successfully partitioned across threads based on size, with large requests on lower index threads. Now let's expand on this example and look at one final experiment to see how things deteriorate when costs aren't actually known up front. With reference to this figure we saw earlier, we're going to run 3 workloads. The first workload will be relatively predictable, with 300 tenants and the same setup as the last experiment. The second workload will replace 1/3 of those tenants with ones whose requests are deliberately variable in cost and difficult to predict. The third workload will replace 2/3 of those tenants with deliberately unpredictable ones. This means that across the experiments, the service is expected to deteriorate and become burstier. Let's look again at T1's throughput. As the workloads become less predictable, weighted fair queuing gives burstier and burstier service. Similarly, WF2Q does reasonably well when the workload is predictable, but also deteriorates as the workload becomes less predictable. Finally, 2DFQ does very well when the workload is predictable, and also deteriorates as the workload becomes less predictable, but by nowhere near as much. We can finally observe how 2DFQ scheduled its unpredictable tenants by once again looking at the thread occupancy. For the predictable workload, 2DFQ is pretty much the same as when request costs were known outright. When things become a bit unpredictable, it looks as though some of the expensive requests are shifting upwards. This is because the unpredictable but small requests are interspersed with the expensive requests, since they were scheduled as though they are expensive. Finally, the effect is even more prominent for the last experiment, where 2/3 of the workload were unpredictable. To summarize, with 2DFQ, we take advantage of the fact that we have multiple threads, which enables us to reduce burstiness for tenants that have small requests. We do this by partitioning requests across thread by size and by co-locating unpredictable and expensive workloads. The result is that as workloads become less predictable and as the range of request costs increase, 2DFQ gives good quality of service where other algorithms rapidly deteriorate. As a result, 2DFQ reduces burstiness and significantly improves tail latency. With that, I will conclude and take questions.
Keshav, I think it's only logical.
Okay. Thank you for an excellent talk. I think it's the best illustration of weighted fair queuing I've seen anywhere. That includes my presentation 89, actually Scott's presentation 89, so thank you for a very good presentation. I had a question though. Your results depend on the predictability of a task. Now, most typical processes have a time-varying behavior, typically I/O blocked and CPU blocked and so on, and the request sizes and the API calls are going to be time-varying as well. So how do you deal with the fact that when you categorize a task as being unpredictable, in fact, it may be an unpredictable phase, and a few seconds later may enter a predictable phase, right? So it's not going to be one size fits all. So how do you deal with that? The estimator that we proposed in the paper for 2DFQ has a decay factor. So our estimates actually decay relatively quickly. What you described, we also observed in our workloads. In the paper, we have some figures that even show what you describe, where there'll be a spike of expensive requests and go back to normal. So there will be a period of time after the spike where that tenant will have degraded latency for their small requests, but then eventually they'll go back to normal. Okay, thank you.
So, quick question. It appears to me that you've described a work-conserving regime. That is, this is a work-conserving queuing system, right?
I'm not familiar with that terminology.
Okay.
So I'm going to say yes.
Work-conserving means that if there's any work
available,
I'm sorry.
I misheard you. Yeah, we are work-conserving. Yes.
Right. So there is some pattern that will drive you to worst-case behavior. That is, you could time if a malevolent party can find the right arrival set to absolutely cause a substantial blip. Okay.
Yeah. So you can sacrifice work conservation in order to guarantee that that won't happen, but if only expensive requests show up and there are no small requests present at that point in time, you're kind of burned.
Right, right. Yeah. Okay, and then the other thing I was just going to mention in this context is there was a lot of work by George Varghese about 15 years ago on striping over multiple links, and I don't know if you saw, a single link made of multiple channels and how to allocate all the different packets over it. I don't know if you've seen it, but if you haven't, some of this is reminiscent.
Yeah, thanks.
Yep.
John?
Is there a complexity result in the paper? Because typically the original motivation for worst-case fair weighted fair queuing was that WFQ was way complex for new demand arrival and departures. You had to recompute the complete time for every round, and that got to be crazy. So worst-case fair was originally, aside from being better, it was like cheaper. But so how does your scheme compare in complexity state?
We thought about this, but we only thought about it in a practical sense. We implemented this, we ran it, we got overheads of less than like 0.1% on our workloads, and we were like, whatever the complexity is, it's fine in practice. Yeah.
Thank you for the previous question. I wanted to ask the same.
Okay.
Okay. One more question.
Hi, Inson from the University of Virginia. I'm wondering whether you consider the dependency between different threads.
So that we have an assumption that there is no dependence whatsoever or communication between threads.
Okay.
That each request is sort of like an atomic unit,
Sure,
which might be wrong. Like if they're accessing the same data, then there could be conflicts between those threads.
Right, so in the future, I'm wondering whether it's easy to additionally consider the dependency between different threads.
So I'm not entirely sure how one would go about incorporating that information beyond looking at something like multi-resource scheduling and then treating some of the application level dependencies as resources, which would then, might shift the requests apart. Sorry,
Thanks.
that's the best I can think.
Thanks for the wonderful talk.
Oh, thank you.
Okay, that's a good point to thank John again for his talk.